Hello everyone. Today we are going to talk about the cantilever beam problem. It's a very important topic in the field of civil engineering. Hi, I'm Rizwan Choktai with Hassan Hanif and we are studying convex optimization. So what is cantilever beam? A cantilever beam is a beam whose one end is fixed and the other end is free, as we seen in the picture. Some practical examples of cantilever beam are like balconies of the modern building and parking sheds. We see in our daily life these kind of structures almost every day. These are the classic examples of cantilever beam. Okay, our objective is to solve the cantilever beam problem that we'll discuss in a bit, but this problem is not easy to solve. There are many methods to solve that problem. In our case, we solve the cantilever beam problem by transforming it to geometric program, and then by using any CVX solver we can solve the problem. So our objective is to transform our problem to geometric program. In order to do that, we must have to understand some terminologies so that we can easily transform the problem. Okay, the first thing we must know of is the monomial functions. What is monomial function? A monomial function is a function that have an expression which contains only one term, and the single term have some positive coefficient c, having multiple variables x, like x1, x2 up to xn, with having exponent ai like a1 for exponent of x1, a2 for x2 up to an for xn, and that exponent a must be a real number, and we can write a monomial function like this. Okay, the next one is polynomial function. A polynomial function is a function which is the sum of multiple of monomial functions. So for the sum of multiple functions, we use summation symbol to generalize the form. So a polynomial function can be written like this. Okay, now what is geometric programming or geometric program? A geometric program is basically an optimization problem of the form in which we have an objective function f0 of x which we have to minimize, along with some constraints like inequality constraints, f of x is less than or equal to 1, and some equality constraints, h of x is equal to 1, where our objective function f0 of x and inequality constraints fi of x are polynomial functions, and equality constraints having hi of x is a monomial function. And the optimization problem of the form like this is a geometric program. Geometric programs are not convex optimization problems. Rather, we transform it to convex problem by changing some variable. So the objective function and constraints are transformed as we change the variable. A geometric program in convex form is written like this, in which we have a transformed objective function that we have to minimize, and subject to some transformed constraints, inequality constraints and equality constraints. So that is the convex form of a geometric program. Now back to our main problem, which is the cantilever beam problem. Let us study the cantilever beam design. As we saw in the picture, a cantilever beam have multiple segments, 5 in our given diagram. So we have total 5 segments. Each segment have unit length and uniform area, having width b and height h, and a vertical downward force F is acting on the free end. We assume that the deflection is very small in the beam and material is linearly elastic with Young modulus E. Now let's try to formulate the cantilever beam problem. Okay, As we want to minimize the total volume of the beam, which is directly proportional to its weight, uh, as the volume of the beam is length into width into height, as we know that, but we use unit length, so for volume we use only two design variables, which are width and height for n segments. So the volume becomes width into height of the first segment plus width into height of the second segment up to the nth segment. Also, we put some constraints on width, height, and their aspect ratio. The constraints are upper bound and lower bound of the width, and upper bound and lower bound of the height, and upper bound and lower bound of the aspect ratio. And these constraints look like this: the width, height, and aspect ratio. We have two more constraints in addition to previous ones. The first one is the maximum allowable stress. We have to limit the maximum allowable stress of the given material, and that can be limited by using this formula. Second one is the vertical deflection of the beam. We must also limit the vertical deflection of the beam, which can be represented by y. The deflection y can be found by recursion that involves the deflection y and slope v of the beam, and their formulas are as follows: the first one for deflection and the second one for slope. Now, to sum up all the constraints and objective function, we can write our cantilever beam problem as given here. We minimize the volume having only two variables, width and height, subject to some constraints on width, height, aspect ratio, maximum allowable stress, and on the maximum deflection. This given form is a geometric program because our objective function is a polynomial, and all the constraints can be expressed as polynomial inequalities. In fact, the first three inequalities are expressed as monomial inequalities, but the rest are polynomial inequalities. So we have formulated the cantilever beam problem as a geometric program. Now that can be solved by using any CVX solver, and we get the results. And yeah, that's it for today. We'll meet you in the next video. Till then, Allah.